Okay, I'm going to be presenting a talk that has two parts. This is based, I should say that this talk is based in part on a talk that I gave at the Japan-America Frontiers of Engineering last year, and based in part on other talks. But I've generated some additional content for this talk, and I'll talk about that briefly. The two halves of this talk, the first half will be a relatively broad overview of the problem of automatic speech recognition. The second half will be a specific application. I'll be focusing on the multi-language automatic speech recognizer that my group developed for the Star Challenge information retrieval competition in Singapore last October, and hence the view on the front of the slide. These are the students and I who went to the competition, and Tom Huang, who was also there, decided not to be in this photograph. And this is the scoreboard as it was during the 25 minutes of the competition when UIUC was in first place. Unfortunately, by the end of the competition, UIUC came out third place in the competition. The first half of this talk will be focusing on a broad, well, let me just go ahead and give it then, and we'll see how that comes out. So the goals for multilingual speech recognition are essentially to take your desktop speech recognizer and to take your automatic teleprompter systems and to apply them to multilingual societies. It's commonly said that the world is speaking English, and the people who say that are the ones who have not tried to get by in small villages in Germany, or say small villages in China, in fact, or in East Los Angeles. Most of the large metropolises of the world are multilingual societies. If you want to get people to talk to a dictation engine in English, they will be doing it with a second language accent. So we want to be able to recognize people who are speaking English with a non-native accent. We want to be able to recognize people who are speaking in their own languages. We want to be able to search through multimedia content which is not necessarily in English, and perhaps find something useful from the content which is recorded in Chinese or in German or in Farsi or in Arabic. So those are some of the goals those are some of the goals for systems of this kind. And the problems are many. By opening it up to a multilingual context, we include not only the usual problems of physical variability. So dictation engines work very well when they use head-mounted, close-talking microphones in a quiet room with a noise-canceling headset. But when you try to record from cell phone speech or from podcast speech or from on-the-street interviews, you have a wide variety of noise environments, a wide variety of reverberant environments, and quite a variety of individual talker characteristics. The categories that you're trying to recognize are actually not terribly precise. There is an international phonetic alphabet, and I'll be throwing it up on the screen later on, but the boundaries between those phonemes depend on which language you're talking, and this has become more and more of a problem for us. And they also depend on what the dialect is of the person who's speaking. The general methodology I'm going to be talking about, although it wasn't put in exactly these terms, can be traced back at least to Fred Jelinek and the IBM speech recognition group in the early 1970s, which was run in parallel with a large DARPA-funded project at about the same time. The general framework is that we want to try to generate. The problem is that we want to try to generate a label string of unknown length. We don't know in advance how many words there are in the sentence, and we want to try to generate that from an observation which is also of unknown length. We don't know in advance how long the observation is going to be. And the general strategy proposed in the 1970s is to perform local classifications or local transformations of the signal in some way to transform the signal to a representation which will be more easily integrated into a global inference engine. The framework that was developed eventually by the end of the 1970s was a hidden Markov model, where this first stage is some estimate of the likelihood of the signal given some kind of intermediate state label, and then the second estimate computes, using a hidden Markov model, the probability of the entire sequence. But it can be generalized to a wide variety of inference engines. So let me talk about each of those components independently. First of all, the transform component is naturally broken down into two parts. And in fact, traditionally, electrical engineers do the signal transform, and computer scientists do the classifier transform. And for that reason, though those two groups often don't talk to each other about the similarities and differences in what they're doing. Signal transforms deal with problems like reverberation and background noise, and sometimes intertalker variability. The model of reverberation is actually so simple that I can put it in half of a line on a slide. We assume that the received signal has been passed through some linear filter that adds echoes, and then to that echoey received speech, we add some kind of background noise. The problem is that H is unknown and random and actually varies as I move my head, and V is unknown and random. And given those, and X is unknown but presumably not random, we would like to get X back, but that's hard to do when you don't know H and you don't know V. But there's a lot that we can do based on that signal model. We also can take into account the fact that the original signal was produced by a human vocal tract, and that severely constrains the kinds of signals that can be produced. The signal must be continuous as a function of time, but not only that, but its spectrum must be at least piecewise continuous as a function of time. And the transitions in that, the abrupt transitions from one piecewise continuous segment to another follow a certain pattern that's dictated by the physiology of the vocal tract, dictated by the fact that there are only so many ways that you can abruptly change the sound coming from your vocal tract. Decades of experience have taught us that the better you can model these front-end processes, the better chance you have of getting good recognition accuracy in the end. These front-end processes are not the classifier, and they don't substitute for the rest of the process. But for example, if you try to construct an entirely data-driven transformation of the input signal, you wind up learning something very much like the spectrally subtracted MFCC, and usually it doesn't perform quite as well because it's not exactly equal to the spectrally subtracted MFCC. So the basic stages usually are denoising, typically something like spectral subtraction, although there's a family of algorithms, dereverberation, which can be something like Kepstrel mean subtraction, or it can be some other kind of inverse filtering, and some kind of perceptual frequency warping to make your system hear what the humans hear from the signal. Here's an example of a denoising process that was developed by Lei-Hun Kim, one of my graduates. This is the word 3 recorded at 55 miles an hour with the windows rolled down in an automobile in December in Urbana. Here's the same signal after beamforming. 3. So this is a combination of signals from 8 microphones in parallel. And you can hear that the noise is reduced, and you can see that the noise is reduced, but it's still fairly noisy. Something critical happens at this point, though. The noise is reduced below 0 dB SNR, and there is a family of algorithms developed by Ephraim and Mala in the 1980s and 1990s that once the signal-to-noise ratio gets below 0 dB, have fantastic results. 3. So we can take that original signal and almost eliminate the background noise from it with a good signal transform. And as you can imagine, the ASR works much better with this signal than it does with this signal. The second stage of transformation I've called classifier transforms. And in a sense, the description of this level of transforms could subsume the initial level of transforms. So the goal is to, I've listed it here as to compute a precise and accurate estimate of the probability of the observation given the state. But in fact what it is to try to take the original signal and to pick out the information which is useful for distinguishing among the labels that you're trying to distinguish. If you're trying to distinguish between the 20,000 words of English, or perhaps more realistically, you're trying to distinguish among the 40 or so phonemes of English, then you want to take the initial signal and transform it into a space where those phonemes are as distinct as possible. This is done using the problems that we face are listed here under the first bullet point under robust machine learning. The problem is that we don't have an infinite amount of training data. Since at least 1990, we've known how to learn an arbitrary mapping of this kind in order to maximize discriminability using a neural network if we have an infinite amount of training data. But without an infinite amount of training data, we have to find some kind of balance between the precision of the model that's learned and its generalization ability. And in fact, that balance depends somewhat on exactly how much data you have and what kind of transform that you want to learn. So things that can be useful include decorrelating and compressing the features so that you have fewer features to model using principal components analysis or just a discrete cosine transform. Selecting the most informative features from an inventory for one system, not the system I'll be describing today, but for a non-speech audio classifier detection system, we've used AdaBoost to help us select the most informative features. To train a linear or nonlinear function that discriminates among the training examples as well as possible. And we've done this using support vector machines or automatic neural networks. It can also be done just using a linear discriminant analysis. And then to train another nonlinear function that has exactly the same properties as this first one. I think that the similarity between these two bullet points is something that's not yet well understood even in the speech recognition community. That in fact, we want to first of all transform the input features so that they discriminate among the labels as well as possible. And then we want to compute an estimate of the probability of the acoustics given what the person is saying. But this probability is also intended to be, in fact, as discriminative as possible among the different categories. We want to try, because in reality, when you listen to me speak, if you go through and transcribe the phones that I'm speaking, you don't say, this phoneme is a T with probability 0.6 and it's an S with probability 0.3. A transcriber says this phoneme is a T and this one is an S and this one is an U and this one is an E. For a human transcriber, those probabilities are always quite close to 1.0 or 0.0. So if we want to accurately estimate what a human would call those probabilities, we're actually trying to discriminate as well as possible among the sounds that the person is producing. So we train a discriminative transform, and then we train a discriminative probability estimate. And even the forms of these are similar, although I've made the forms less similar by the way I've written them on this slide. One of the methods that we've used for performing the first stage transform is to use a bank of support vector machines, each of which is trained to discriminate one of the phonological distinctive features. For example, voiced versus unvoiced, or front vowels versus back vowels, or alveolar TD versus GK. And we do that by accepting as input a bank of acoustic features. And in a system that my student Sarah Boris developed, this was actually performed over 99 different acoustic inputs, including simple spectral summaries, including summaries of the autoregressive fit, the formant frequencies, and including auditory modeling features, over a sequence of 11 consecutive centiseconds, 11 consecutive 10 millisecond windows. We then pass these through a radial basis function support vector machine, which means we have some width for each of these kernels, and we add them up with some weights alpha sub dv, where those are trained using a maximum margin criterion. These features then come out to be very good at estimating, at outputting a 1.0 when the desired phonological feature is present, and a minus 1.0 when the desired phonological feature is absent, but not perfect at doing that task. Then we want to somehow integrate that with knowledge of the relationship between phonemes and words. And in order to do that, we need to do an impedance match. We need to somehow match this information with the kind of information that the inference algorithm expects. The hidden Markov model or the dynamic Bayesian network expect their information to be given to them in some format like this. They expect a log probability of the acoustics given some intermediate state variable. And so we train that by defining the way in which phonemes are made up of states. And then, given knowledge of the way in which phonemes are made up of states, we can compute an estimate of this log probability, and that's computed as a mixture Gaussian, which actually has exactly the same form of that. But now I've given you, instead of the mixture Gaussian form, I've given you the logarithm of the mixture Gaussian form. And the reason I've done that is because that's the way it's usually computed. The most computationally efficient way to do this is usually, rather than adding together a bunch of exponentials, we add together their logarithms using a softmax function, the softmax being the logarithm of the sum of the exponentials of its arguments. And there are computationally efficient ways to do that without exponentiating. So if we can take the softmax over 63 or 64 Gaussians of the probability of that Gaussian, this C sub qk is similar to the alpha parameter up here, times the times the log probability of the Gaussian itself. That is to say, the log probability of its precision minus the precision times the square of the difference between the distinctive feature and the mean of that Gaussian. The precision being 1 over the variance, corresponding to the gamma term in the support vector machine. I put these up specifically for this talk because these are 2 of the 3 places where we need CPU cycles. The de-reverberation and the denoising are actually are still running in better than real time on modern machines. They're not too computationally intensive, but if the support vector machine is allowed to learn, if we're allowed to learn 50 different support vector machines, each of which has a 500-dimensional input and 500 support vectors, 500 support vectors, then this is a fairly intensive computation even during test time. And if the Gaussian mixture model is allowed to have 64 Gaussians per state for 2,000 different, acoustically different state variables, then this is also a computationally intensive task. We can train these things using available algorithms and by throwing things into the cluster for a couple of days, but we can't run test in real time. All right. There are some things that I glossed over in the previous slide, just some design decisions having to do with the classifier transform that are also relevant to the problem of inference. The problem of inference is really the problem of going from variables that it's possible to classify locally to variables that we actually care about. Usually we don't really care which phoneme is being produced at a given time. Usually what we care about is the word string. And so the design decision really comes down to figuring out what are the state variables, what are the variables that can be classified locally and yet have as nearly as possible a one-to-one mapping between a state sequence and the words that you care about globally. In automatic speech recognition, the thing that you care about globally usually is the sequence of words that were spoken, but in information retrieval it's something quite different. You want to know which segment in the database matches the query. In a computer-assisted language learning task, you don't really care what the word string that was spoken is, as long as you can identify the ones that were produced with a pronunciation error. All right? It's very difficult actually to define exactly how these criteria differ from the first criteria in a way that leads to useful algorithm improvements, but we're working on it. The states, on the other hand, have to be something that you can get locally. So typically these are something like phonemes, or more typically they're subphonemes. A stop consonant, for example, includes a silent period, and then it includes a transient burst, the sound in the T, and then it includes some aspiration, some H sound that occurs between the T and the following vowel. And so because the maximum number of acoustically compact states that occur in any of the phonemes of English is 3, we just arbitrarily typically assume that every phoneme is composed of about 3 states. But it doesn't need to even be a scalar variable like that. It doesn't need to be the first or the second or the third state in the Q sub t. In some of the systems we've developed, this is a vector of articulatory states. So we might say that the thing that can be classified locally is a vector of variables, one of which tells you where is the tongue blade right now, one of which tells you the degree of aperture of the lips, one of which tells you the degree of voicing, and one of which tells you the degree of nasality in the current state. Another way in which we have vectorized this problem is to say that one of the variables might tell you one of the variables might tell you the phoneme being produced by one talker, and one might tell you the phoneme that's being produced by another talker who is talking at the same time. And then the inference algorithm then is some kind of parametric model of the probability of a particular state sequence given a particular label sequence. And there are a useful set of families of these. Probably the first one was the hidden Markov model, and that's been recently generalized in 2 ways. It's now known that a hidden Markov model is a special case of a dynamic Bayesian network. It's also a special case of a finite state transducer. And I'll be focusing in this talk more on the finite state transducer interpretation because that's what we've used for information retrieval. So just for example, just for the problem of automatic speech recognition using a hidden Markov model, the inference algorithm is the Viterbi algorithm, and this is the third place where we consume a lot of CPU cycles because these numbers are so large. What we want out of the Viterbi algorithm is the log probability of basically of the word given the acoustics and marginalized over all of the possible subword states. But since that's hard to compute, what we compute instead is the joint probability. The joint probability of the acoustics and the subword states and the word sequence we get at time t by looking at the probability of the acoustics given the current given a current estimate of the subword state, plus the maximum over all of the possible preceding probabilities, the preceding output probability plus some kind of transition probability. And this is a dead simple computation for each of these individual computations. The problem is that we have 64,000 or 65,000 words in the vocabulary, and we have 2,000 different acoustic states. And even though most of these transition probabilities are null, because you can't say the word cat and have an S in it if you're speaking English, even though most of these probabilities are null, still enough of them are non-null that that this becomes a computationally intensive problem. Basically, it's this one equation applied 65,000 squared times per centisecond. All right. So so that's the general overview of automatic speech recognition, with a special focus maybe on the three places where I think current implementations are too CPU intensive to run in real time. Now I'm going to focus in particular on the problem of language independent phone recognition, which we used for the information retrieval task in the STAR challenge. So the algorithms that we used at each stage, in the signal transform we used a voice activity detector and then a relatively standard perceptual frequency warping. The voice activity detector was just used to endpoint the signal. We should have but didn't have time to implement any kind of denoising for that task. The probabilities were estimated using Gaussian mixtures and giving a likelihood vector, the probability of the observation that we know exists at time t, given any one of the different of the 2,000 or so subphone states that were available to the system. And then the inference algorithm was a hidden Markov model implemented using a fairly old-fashioned algorithm, just a token passing beam search Viterbi algorithm, in order to give us the best label sequence. The tricky part about this one was that it was language independent. We weren't told the language of the query or the language of the or the languages of the database before the day of the competition. So so we found out by the time we find out which languages we're going to have to recognize, we have 48 hours to turn in the results, or 4 hours in the final. So what we did was we picked out the phonemes from the International Phonetic Alphabet for which we actually had some training data. Here are the consonants of the International Phonetic Alphabet. These are fa, fa, tha, sa, sha, 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 ha, ha, and ha, something like that. I'm not very good at the pharyngeal sounds. I guess the q is not too bad. That's the q in Cairo, for example, in Qahira. Right. We have actually training data for all the fricatives. We have a database that has 11 languages in it. We didn't have any training data for the labiodental nasal. And we actually threw away the training data for the ejective stops because that doesn't exist in any of the languages of Southeast Asia. The implosive stops actually do exist in some of the languages of Southeast Asia, but we had no training data for them. And then the vowels were, the vowel space is actually not quite as, the space of the world's vowels as defined by the International Phonetic Association is not quite as big as the space of consonants, but that's because they completely ignore diphthongs. So sounds like ow or a or o don't exist in the International Phonetic Alphabet except as sequences of multiple phonemes, but they're individually distinctive and hard to tease apart. They're hard to segment in many of the languages of Southeast Asia, and in fact in Chinese as well. Other vowel sounds that we had included a series of retroflex sounds, the let's see, this is r, and more or less. The training data included data from 10 languages in the end. We started with 12 and threw away 2 because of transcription problems, and included 95 hours of speech sampled from a much larger set of corpora. one of the interesting problems that we ran into was that we had data from 10 languages, but we didn't have data from the right dialects. So we actually performed quite poorly on the Mandarin recognition, despite having Mandarin as one of the languages we were training on, because our training database included Beijing Mandarin, and the test data was Singapore Mandarin. So difference in difference in dialect matters. There are the databases. Is there anything I need to tell you about here? We did actually explicitly model non-speech tags, including silence and including some punctuation marks, which were included as possible context variables that might affect the phones being produced to the left and right of that variable. The data has to be prepared, and actually the most interesting, one of the most interesting preparation for me was the Urdu database, because we'd had no dictionary for Urdu, but there are diacriticized Urdu dictionaries available on the web. A diacriticized database means that the raw form of the standard form of Urdu includes no vowels, of course. But if we can look on the web and find something that has the same consonants but also has, you can see the little dash underneath the h there, whatever that sound is, that represents the E in the final syllable. So I can play these so you can hear what they are, because I don't know Urdu well enough to say it myself.
Sahiba, Swaika, Sahiba, Swaika.
So something like sahiba and sahiqa. Both of these actually have the same vowels in them, but that one we found something marked on the web, and this one we didn't. And so we can apply a set of rules that then converts the phonetic characters of the Arabic script directly into IPA phones, or in this case we can convert it into IPA phones with an unknown vowel marked in it. So the unknown vowel is this SV symbol. We just don't know what it should be. All right, and then that's not enough, actually. So that gives us maybe 200 different phones, or 300 different phones, depending on how rich the set we want. But in fact, the T in tree is quite different from the T in that. And we want to be able to model that difference. We don't want to try to force the classifier to learn that those are the same thing. If we can tell it in advance that they're different, it's a lot easier to learn a compact distribution than it is to learn a multimodal distribution. And so we do that with a series of steps. First of all, something quite standard. We call it a triphone. We say that the T in that soup is the T which is preceded by an A and followed by an S. Second, we mark the lexical stress. The E in reek is longer than the E in recover, so we called the E in reek the stressed version of the E that's preceded by an R and followed by a K, and the E in recover is the unstressed version of the E that's preceded by an R and followed by a K. And second, we try to model intonational phrase boundaries, but we don't have prosody transcribed in this corpus, so we did it by using a set of proxy variables, namely punctuation. For the databases that had punctuation, periods and question marks and so on, they were included as context variables for the surrounding phones. The N in I'm done is typically pronounced with a duration that's twice as long as the N in the phrase done yet, so we can model the difference by including the period as actually a context variable that influences the way in which that N is produced. Finally, it's not clear what is the best way to model language, but we wanted to be able to because we know that we're going to have data in the test case that are from languages that we don't know in the training data, we wanted to be able to model, to tie our models across languages, but we also want to make it possible to separate out languages that have substantially different implementations of a phoneme from all of their neighbors. And so this is an example of the difference of a very salient difference.
They'll sit there and ask me to atone for my sins.
This is a Middle Ohio dialect of the O and a tone.
Tone.
And you can hear that it's kind of pronounced with this oo offset at the end, as tone. All American English speakers talk that way within kind of an oo offset. This is a rather pronounced example. In Japanese, for example, that oo offset doesn't exist.
その後に
So this is short, but even if it was longer, in fact, there would be no oo offset in that tone. It would be a completely static spectrum. And so we want to make it possible to call these different things. We want to make it possible for the classifier to use different symbols for those two different phones. The problem is that if we if we use all of those variables to subdivide the training database, then we wind up with one or maybe as many as 5 examples of each of our labels, and that's not terribly useful. It's hard to train a reliable classifier from one training token, and so we back off from that very fine-grained subdivision using a relatively standard method, but applied to a wider variety of variables than is standard, using a classification tree that takes all of the middle states of the phoneme ah, for example, and subdivides them according to variables. And each of these subdivisions is made such that the conditional entropy of the tokens in the leaf node, given the leaf node label, is as small as possible. And if the probability density function of the spectrum is Gaussian, then that turns out to be just a measure of the variance of the Gaussian, of the discriminant of the covariance matrix of the Gaussian. So this is all done halfway through the training. We perform the training of the parameters in order to get estimates of each of these leaf nodes, and then we tie the leaf nodes together in a hierarchical system of this kind, such that if we such that we know that we have enough training data to train each of these leaf nodes, but not to subdivide the data any further. The tree then chooses the divisions that make the biggest difference in the data. And it turns out that the biggest difference among the different implementations of ah is whether or not the phoneme is being produced in Mandarin. The Mandarin implementation of the low back vowel is different from all of the other languages in our training database. If it is Mandarin, then you want to know if it's preceded by a y, and if it's not Mandarin, you want to know if it's preceded by a voiced phoneme, and so on down the tree until finally you get to a leaf node where the number of training tokens, finally at this leaf node, the number of training tokens in the database is down to some threshold, so we can't subdivide the data anymore past this point. All right. These were tested in 2 experiments. One was a phone recognition experiment, and one was an information retrieval experiment for the STAR challenge. The phone recognition experiment used language-independent triphone bigram language. Triphone bigram. Actually, there's a problem with that. It used a bigram language model, which was not language independent. It used triphone acoustic models, which were language independent. It used most of the input was standard PLP plus delta deltas using a continuous distribution HMM with 11 to 17 Gaussians per state, and the vocabulary size was limited to be the top 60,000 most frequent of the triphones. There were 140,000 that were actually in the tree, but the other 80,000 were discarded, were mapped back to their monophones. Actually, the results varied quite a lot depending on the language that we run it on, and it seemed to depend primarily on whether the speech was broadcast news or spontaneous speech. So when we have broadcast news speech, we get 50 to 90% accuracy. When we have spontaneous conversational speech, accuracy drops to 40 to 50% for this phone recognition task. The other way in which these were used was in the information retrieval task, and the goal here is to not make a firm decision as to the phoneme content of an utterance. Rather, we build a lattice of transcription alternatives, and then we try to match that lattice of transcription alternatives with the phones that are specified in a query. The queries were given to us without naming the language in which the query was spoken, and therefore without naming what words were being spoken, because that would give away the language. Instead, the query was given as a sequence of phonemes in the International Phonetic Alphabet, the alphabet that I showed you a few slides ago. So we had a sequence of queries. Let's see, do I have an example? Here's an example. We would get one of the examples was Rogucha, which we didn't have the tones that I just read marked on it. so we didn't know in advance which language that was, although having quite a number of Mandarin speakers on our team, it was easy to guess. The methods that we used were, so here's a summary of the methods that have been used for information retrieval. The most common method, the method that Google and Yahoo admit to using is basically a summary statistics method, often called a bag of words concept, where you have a listing of the frequency of a word of every word in the English language in a particular document, and you try to match those frequencies against the frequency of your query. Most of the large search engine companies are using something a little bit richer than this, but it mostly boils down to some kind of summary statistics. The algorithm that actually won this competition, that beat our system, was an exact match. That is to say, they computed the one best ASR output from the audio, and then tried as well as they could to match that to the IPA transcription of the query. And my opinion is that won because the competition was performed in 2 hours on the final round was performed in 2 hours on stage, and that algorithm was just much faster than the algorithm we developed. The algorithm that we developed apparently performed better in the preliminary rounds of the competition when we had 48 hours running on a 1,000-node cluster in order to running on one 100-node cluster, one 32-node cluster, and 1,000-node cluster. There were actually 4 rounds to this competition. There were 3 elimination rounds, each of 48 hours duration, and the output of those 3 rounds was 5 teams who were selected to go to the grand finals on October 23rd in Singapore. The tasks, there were 2 video tasks which I'm not speaking about today, but were given an image category, find the examples, and there were 2 audio tasks. The first was, as I've described, given an IPA phone sequence to find all of the audio segments that contain that phone sequence. The other was given a waveform that contains a word or word sequence spoken in some language, in any language, find audio segments containing the same word, not containing that particular utterance of the word, but containing a word which would be recognized as the same word by a speaker of that language, whatever that language happens to be. All right. And here are the oversimplified results. On round 3, actually I think we were tied for first on round 3. Well, we were either tied for first or tied for second on round 3. On the grand final, we came in 3rd place. And I believe that the critical difference was that on rounds 1 and 3, we had jobs running for 48 hours continuously on the TLEAC cluster, and in round 1 also for about 18 hours on 3 of the NCSA clusters. And so we had, I estimated at one point, 48,000 CPU hours per round in order to run this transform and infer set of algorithms. On the grand final, we had three computers on stage that were running for a total of 2 hours in order to compute 8 queries. There were 2 audio queries from each of the 4 national languages of Singapore. So I think that there's some interesting open research. The best algorithms in if I go back here, not only ours, but in fact all of the best algorithms in round 3 of the competition were more complicated lattice-based transform and infer algorithms. That is to say, the ASR generated a lattice of potential matching hypotheses, and then the search algorithm was able to search through the inference algorithm was able to search through the lattice in order to find the best retrieval. In the grand final, the best algorithm was an exact match algorithm. As I described it, they generated the one best output from the ASR and tried to match it to the query. So there's a big difference between having 48,000 CPU hours and having 6 CPU hours as to the kind of performance that you can expect from any particular algorithm. So computational complexity of the algorithms is an area that we have apparently not paid enough attention to. The other is really the same problem, but with a different objective function. The different objective function being essentially the trainability of the parameter set, the trainability of the acoustic model and the language model. The more you know about the problem, the better you can define the problem, the more precisely you're able to learn from a training database of a given size. Right. So So it's possible with an infinite amount of data to learn any mapping using a neural network, but we never have an infinite amount of data. We may have at most 3,000 hours of data, which is quite a lot. In this task, we had 95 hours of data. So we need some way to balance between the precision of the model and its generalization ability, and one way to do that is to bring to bear as much information as we have about the task description. Okay. Oh, and I wanted to throw in something on a completely different topic. This is an existence proof of the fact that ASR can actually beat human listeners. This is the problem of automatic recognition of the speech of talkers with cerebral palsy. And the ASR in this case has an unfair advantage. We are using talker-dependent ASR with a limited vocabulary size, and we're comparing that to the recognition accuracy of human listeners who have no familiarity with the speech of people with cerebral palsy and don't know from what vocabulary the words are selected. And with constraints of that kind, the ASR soundly trounces the human listeners. So, for example, human listeners are getting 6% accuracy for this talker, and the ASR is getting an average of around 50 or 40% accuracy. It's not an unreasonable sort of comparison, though, because we have these talkers who are getting, say, I think this talker who has a 29% accuracy as rated by unfamiliar human listeners, and we ask her, and she can't move her hands actually, so she can't use a regular keyboard. So we ask her, well then, how do you she's a university student. We ask her, well then, how do you type your papers, your term papers for class? And she says, oh, well, I dictate to my mother. So, so if the ASR can become as familiar with the speech of this talker as her mother is, then we have a chance of performing as well as her mother, or at least somewhere in that general ballpark. So we want to be able to, if the ASR knows more than the human, it can beat the human, so we want to build better knowledge into the system, essentially. And I guess that's my take-home message. Any questions?
So we have time for a couple of questions. Why don't we take a few from the audience here, and then we'll see if there are any questions from the remote participants. So, go ahead, Mark.
Okay, thanks. Please go ahead.
I have a question about the result of competition, and you showed that the six computers with only 2 hours. So how is the quality of the result of those winners? Is that good result, or if you compare with all those algorithms, if they are equally bad, so there is no sense of having a comparison if 6 hours is too time? So I just wondering how's the quality of
So the question was does having only 6 CPU hours significantly compromise the quality of the results such that all the different algorithms were equally bad when you have only 6 hours to perform the testing rather than 48,000 hours in our case? And the answer is that I don't know because A*STAR didn't publish the actual accuracies. I suspect that all of the algorithms were quite bad.
Related question is, if you are given as much time as you can, is the performance good or bad?
If you're given as much time as you can, is the performance good or bad? The performance gets better the more training data you throw at it, but I wouldn't call the best performances that we've gotten. I wouldn't say that they're good enough yet. We're not. So there's a bit of a. This is a place where there's an interesting disconnect between academic and corporate research in automatic speech recognition. In corporate research, when users are using an ASR system, they expect the system to not make mistakes. They want 99% accuracy. A system which has been a technology which has been refined to the point where it can get 99% accuracy is not really that interesting to me as an academic researcher. So I focus on problems that are more difficult, like, for example, multilingual speech recognition, where the accuracies tend to be more like 70% than 99%.
Just to follow up a little bit, the A*STAR challenge, the tasks are actually very difficult. The quality of the speech to be recognized is very poor. So
Yeah.
I think we still need to work on the algorithm. Like, give infinite amount of time.
Yeah.
Probably still cannot do too well.
Yeah. So the comment was that in the STAR challenge, there were a lot of problems besides just the fact that it was multilingual. The quality of the audio that we were trying to transcribe was actually very poor, and that's a good point. One example of a problem that that we had with those data that we've not yet had any time to look at is that being broadcast data, many of them were mixed. Much of the data was mixed with music, and we were asked to recognize words that were spoken in a music background, and we didn't measure the difference between recognition in a music background and recognition in a silent background for this task. But I've done that comparison once before. We can get digit recognition if you just say there are 10 digits, which of the digits was spoken. We can get digit recognition accuracy easily better than 99% accuracy in quiet. But when you mix music with it, the best reported accuracy that I've seen is a paper that we published in 2002 or 2003, which was around 48% accuracy. The denoising algorithms that I described might have been useful, but they're actually designed for steady state backgrounds like fan noise or wind noise. There's no good model yet that I know of for recognizing speech in a musical background.
I think we have a remote question. Wanna get it?
Okay.
The student from Mississippi State has a background in speech recognition and parallel processing.
Great.
What do you think are the potential areas where parallel processing capabilities of multi-core processors can be applied to improve speed up?
I think that.
Would you mind repeating the question?
Sure, I can repeat the question. The question was, what are the areas where parallel processing and multi-core technologies can be applied to speed up speech recognition? And I assume the question means, what are the areas where that can make a big difference in the performance results that we get? First of all, I'd like to separate training versus test phase. There are ways in which it could be applied during training, but I haven't been focusing on them very much in this talk because the training algorithms usually we run once and then we have a set of trained parameters and we can use those for testing, and therefore we don't mind so much if training takes a week or a month on a large cluster. Usually the low-hanging fruit, probably the place where we need processing the most, is during the test phase when we have. If it's in a user system, the user starts dictating and expects the machine to run in real time and to pop up words on the screen. If it's in a competition of this kind, we have a certain limited number of hours in which to come up with a result. So the low-hanging fruit, at least, is is things that can be applied to running the recognizer in test phase rather than in training phase. And fortunately, there's actually several things that can be applied to both training and test, but the three sub-areas that I think have the most promise are the three for which I showed equations during this talk. Number one, if you're going to do something like a tandem system, which was a word that was coined at Berkeley to describe the first of those transforms that I showed, they used neural networks in order to create a discriminative transformation of the signal that can be better discriminated by the back end. We use support vector machines and a variety of other technologies. Number two, the mixture Gaussians, just because there are so many of them. It's a relatively straightforward computation. Computing a Gaussian is computing a dot product followed by an exponentiation followed by a log sum. But it's done thousands of times per centisecond. And number three, something like the Viterbi algorithm, computing a maximization over the 65,000 possible words that might have occurred in the preceding time step. Question?
How much of this is embarrassingly parallel? You said you ran your algorithms on these huge clusters. Are you using any sophisticated parallelization technology, or was it just the same thing?
Actually, no. For training,
No, not
you know.
for training.
So for testing, well, actually, yeah. Even for testing, we used a very coarse-grained parallelism on the clusters. For both training and testing, the parallelism that we used was to divide all of the files up and to run the same operations on each of the different. So the audio, when I say that the audio is 95 hours for training and is the testing the database from which we had to retrieve segments was 18 hours. 18 hours of audio can easily be divided into 30-second chunks by just looking for silences.
Okay, so this is because of your problem situation where you were actually trying to find instances. You were trying to mine a large piece of audio, and so that was all in the sense.
Yes, that's right.
But I assume you can think about problem formulations where each of those computations would be, you need to do those in clinical time or
Right.
in real time.
So you can think of what we've implemented is coarse-grained parallelism. You can imagine the situations that I just described in response to the student from Mississippi State are all cases where fine-grained parallelism would also be useful. If you had a single computer sitting on the desktop that's supposed to output words in real time to a human user, that would benefit. If it's currently running in real time, as many commercial systems are, then you could have a system that's 8 times more precise by running 8 times as many operations, by running 8 times as many Gaussians. If it's currently not running in real time, as most of our systems are, then maybe you could bring it to real time by using fine-grained parallelism, basically taking the dot product, which is that Gaussian, and turning that dot product into 8 parallel multiply-add operations. So I think that that could be combined with the coarse-grained parallelism. If we were trying to retrieve segments from a database of 18 hours, we could chop that data into 30-second audio files and send those out to 1,000 different computers. But then on each one of those computers, we could be computing the Gaussian using a form of fine-grained parallelism, if that had been implemented. Does that answer the question adequately? I think Arthur was next.
So it's kind of related to what you were asked. If you're trying to speed up recognition of a single utterance, it seems that the Viterbi part is the slow part. Do you know if the Viterbi algorithm can be parallelized in a nice way, and whether any groups that are working on multi-core machines are really?
So the question was if the question was assuming that the Viterbi algorithm is the slow part of the testing, and that's probably a good assumption in many cases, then is there a way to do fine-grained parallelization of the Viterbi algorithm? I don't know of anybody who's done that yet. I haven't seen even research in progress on that. I think it's possible because, for example, I think it's possible because you're calculating the path cost from 65,000 possible previous states to 65,000 possible current states. So in a sense, you have a 65,000 squared operation, but I think you could parallelize that on either the from states or the to states. So one way to compute a max operation is to compute all of those additions and then bring them back to the main core and find out which one is the maximum. That would be parallelization over the from states. You just take all 65 for given a particular to state. You take all of the 65,000 possible from states, throw them at the parallel system to get their additions, and then bring them back and find the max. Conversely, you could have each one of your parallel cores computing one of the to states, in which case you would then go sequentially through all of the from states and take, for each of them, throw the from state at it and see whether that from state is better than any of the from states it's previously considered. Wenmei?
So, Mark, can you describe your development process? Let's say leading into that competition, do you have a set of these program modules that you're kind of using different combinations of input or training or something, or you're actually being limited by how quickly you can redevelop or implement new algorithms or new modifications of the algorithm leading into that competition?
Yeah. For this competition, okay, repeat the question. So the question was, during the development process for this competition, let's see if I can rephrase the question. How much of our development used existing code, and how much was what required us to develop additional code, and what was the time limiting factor, I guess, in terms of code development. The time limiting factor. So we didn't have time to do any code development. That's not quite true. We actually Xiaodan developed the information retrieval algorithm during the months preceding the competition. But all of the ASR training and testing algorithms used a large number of sub-blocks that are open source and distributed by our colleagues around the world, combined together with a small amount of original code that tied those units together. And the reason for that was that the the real bottleneck in terms of time for us, given only 4 months to prepare, was just learning the parameters of the acoustic model and of the language model from data. And so we wanted to spend time focusing on that rather than focusing on original code development. Original code development is always of interest, but you have to be certain that that the advantage relative to what's available open source is enough to justify the programming time.
Mark, is it, if you sort of look at improving the accuracy of an automatic speech recognizer, is there opportunity in trying to bring in machine learning if you're trying to understand what the speaker is saying? You know, if you incorporate machine learning, can you improve the recognition?
Yeah. So the question is, can you improve the recognition rate using techniques from machine learning? And
well, actually, I mean,
maybe
let's say
rephrase.
the task is not only to recognize what's being spoken, but to understand what's being spoken. If that's the objective, is there some feedback that you get from the understanding process to improve the recognition rate? So the question is actually about speech understanding, not speech recognition. The question is, can you use feedback from the speech understanding task in order to improve the recognition accuracy? And I like that question because actually we're one of the few labs in the world that's actually been able to demonstrate an improvement of recognition transcription accuracy by including a component of speech understanding. The answer from most labs in the world is that the best way to perform speech understanding is to do transcription and then to throw the transcribed text over the wall to the language understanding component. We have actually demonstrated improved transcription accuracy by incorporating a very limited form of speech understanding, that is, by incorporating some knowledge of the possible prosodic structures of the utterance, which is to say the phrasing of the words into intonational phrases, the prominence that one gives to particular words. This is not semantics, this is not meaning, but it's related to higher level language structures that are not usually brought into the speech recognition task. So we model essentially which words are important, and we model which words belong together in a group. And by doing that, we've demonstrated small but statistically significant improvements in recognition accuracy. Thanks. Well, I think we've asked Mark plenty of questions, and we want to thank you again for a very informative and enlightening seminar.
Thank you. Thank you very much.